Number 1. A .096 diameter circular coil of wire with 50 loops is in a 1.1 Tesla magnetic field. If the loop is removed from the field in 1.5 seconds, what's the induced EMF in the wire? In what direction is the induced magnetic field? In what direction is the induced current in the wire? Okay. So I kind of want to show you how to solve these, but I also want to kind of give you options as far as like what answers you would get and what those answers would look like. So first things first, let's write down what we're given. We're given the diameter, which I'm going to be honest, not really sure why I gave you diameter instead of radius. Because you need radius. Guess I was just feeling in a foul mood or so. So we need to know, we'll just write down what we have. We have the diameter to be 0.096 meters. We have 50 loops, which is n, the number of loops. It's just 50. It's in a 1.1 Tesla magnetic field. And the field is removed in 1.5 seconds. So we remove the field all the way in 1.5 seconds. Okay, so we're solving for EMF. So EMF equals negative NA delta B over T. So N is the number of loops, which is 50. A is the area, and at the bottom I gave you the area equation. So a circle is pi r squared, square is length squared. And those are the two shapes we'll do. We'll do squares and circles. Okay, so the area is pi r squared. So it's pi times the radius squared. So the radius would be 0.48, half of that. Sorry, 0.048. Okay. And it's change in magnetic field. So it says it's removed. So if you see the word removed, that means the field goes down to 0. So all the way out. Okay? So that means the change in magnetic field is 1.1 Teslas because it changes from 0 to this. Or in this case, it's this to 0. So it's removed. So that's going to be, I don't know why I made that equals. It's going to be a negative delta B, so negative 1.1. And again, negative is because it's removed, so it goes down. So you lose field, you don't gain field. So you lose field instead of gaining field. And then the time is 1.5 seconds. Okay, then we just multiply everything. So 50 times pi times 0.048 squared times 1.1 divided by 1.5 gives me a voltage of 0.265. And notice I got a positive answer, and the units for is volts. I got a positive answer because I got a negative and a negative. So the negatives cancel, and I got a positive answer. Yeah.
So would the numerator always be, or delta B, would that always be negative?
No. So here's where it would be positive if I put a magnet into it. So if I insert a magnet, it would be positive. If I remove the magnet, it's negative. Because the magnet goes down. One last thing I want to mention, because it's not on this one, but it could be on other ones. If I specifically say a south pole, which I forget if I do. I don't have it on any of these problems, but you will see a problem with the south pole. All you have to do with the south pole is set it up normal and then make your answer opposite. So like if I get a positive answer and I said this was a south pole, I just make my answer negative. And if it was a negative answer and I said it was a south pole, I make it positive. That's all you have to do. That's all you have to do. Okay, so I'm removing field. I'm pulling field out. And so if I'm pulling field out, that's going to induce a magnetic field that's in the opposite direction. So what direction is the induced field? So I'm removing the field. That's why I got negative here. What's my answer? Positive, which is in. Positive answers are in. Negative answers are out. So if I remove the field out, the opposite, negative, from Lenz's law, would be a positive answer. So what direction is the induced magnetic field? It's in. That's it. That's all you have to do. So you can use the answer to tell you if it's in or out. Positive will be in, negative will be out. But use your big old brains to help you too. So use your big old brains to say to yourself, okay, what's it doing? I'm removing the field, so the opposite direction would be the field going in instead of the field going out. So remember, they're always opposites. So you can use that to double check and say, okay, did I get a positive answer? Yes, I did, so it's in. Okay. And lastly, see in what direction is the induced current in the wire. Okay, this one is kind of tricky. So this is the right-hand rule, the curly Q thumb hand ringing one. Okay, because we're talking about fields and wires, fields and current. Okay, I like to use a visual aid, a roll of tape. Okay, here's how I do it. I say to myself, what's the direction of the change? Out. So what's the direction of the field? In. Okay, your field are your fingers. So what I do is I take my fingers and I put them in to the loop. Now, if you don't have a loop of tape handy, you can always just use your fingers. You got to be a little careful about sticking your fingers into your other fingers, or your friends are going to laugh at you. But that's the idea. Like, think of it as a coil of wire, and your field is going in. So the field is going in. So what I do is I wrap my fingers around, and I lay my thumb across like I would. And what direction is the current going? Around the loop, clockwise. And that's my answer for the direction of the current of the wire. Okay? So to show it to you one more time, here's my loop of wire. We said that the magnetic field changes in. So I go ahead and I take my field and I put my field in. Okay? Then I curl my fingers around to grab onto my loop of wire and I lay my thumb down. My thumb is the direction of the current. That's the right-hand rule. So it's going around this way, which would be clockwise, would be the answer. Okay? So let me just give you some options for what your answers could be for these two questions, because you're going to notice what's the EMF, what direction is the induced field, what direction is the current. This one's a little different. How many loops are there? What direction is the induced field? What direction is the current? So you're always going to get a B and a C. Here's your options. For B, your answer is always going to be in or out. Those are the only two options. In or out, that's it. And for the direction of the induced current, it's always going to be clockwise or counterclockwise. Clockwise or counterclockwise. So, what if the induced field had been out? If the induced field had been out, Here's my field coming out of it instead of going in. Wrap my fingers around, curl my thumb around. Counterclockwise would be the direction of the current. Sarah, put the phone up. Thanks. Okay, it's in the opposite direction. So, people have asked me in the past, is in always going to go with clockwise and out always going to go with counterclockwise? Yes.
So if it's in, it's clockwise?
Mm-hmm. Yeah. So if you can remember that, then you can just go that way.
Yep. They
Yep.
call me a master physics man.
That is what they call you, the master physics man. Yeah. So that's the idea. All right. Any questions on how to solve this problem? Yeah.
So if, so you're saying, so number one, it says the loop was removed from the field.
Correct.
That means it's going out, and that means the magnetic field is going in.
Right. Because they're always opposites. So whatever I do, the induced field is opposite.
Okay.
So I did out, so the answer is in. That's why I got a positive number here. Remember on that lab, things always went in the opposite. Like when we put the north in, it went to the negative side. Same thing with this here. Yeah. Caden, was that your question?
No.
Okay, I'll come to you here in a sec. All right, so I'm going to give you the rest of the period to work. You just got 2 problems. It's the same basic setup. You're solving for something different than EMF in number 3, so just be careful about that. Also, be careful it doesn't go to 0 in this one, so you're going to have to find the difference between the 2 magnetic fields. But other than that, it should be pretty straightforward. If you have questions or need help, let me know, and I'll be happy to help you. And we'll go from there.
Thanks for the